Okay, so I figure out that maybe using the OBS is a little bit more complicated than it already is. So I figure out that maybe the best way to this presenting my slides by using this Zoom, and then from the Zoom I'm going to upload to YouTube. So hopefully you all will be able to accept it, and then you can still see the things, and then you all can still see the same. I hope that you all get the same results as the Zoom as these things do. Okay, so hopefully you all are okay with it. Okay, so with that annexation, let's begin our discussion. Okay, so a boss model represent. We are going to continue with the chapter 2 set structure questions. With question number 1, a boss model represents hydrogen atoms is shown below with a several electron transition depicted by the arrows. So which transition is the diagram above is an absorption. So the absorption is from low energy levels. It must be from low energy levels to high energy levels. So you can see from here, this is the only place where you have low energy level to high energy level. So it is represented by the arrow A. Okay, so A is the one that shows that it is an absorption spectrophotometer. Then we have B. Figure below shows some spectral line of line series in the hydrogen atoms. So in figure labels, which line are produced by B and C. So here, if you look carefully, line B is from energy level number 6 to energy level number 1. So it should be the difference of energy level is 5 lah. So it should be the 5th line. Okay, while in C, it is from energy level equals to 4 to energy level equals to 1. So the difference of energy level is 3, so it should be the 3rd line. So based on here, so how are you going to deduce which one is B, which one is C? So this is the first line, it is usually the first line, and the one which is a rough one is usually the last line, Lyman series. Okay, so in here, therefore your B is here. This is your this is your C, the 3rd line. Okay, this will be your B, the 5th line in the Lyman series. Okay, so this is how you are going to answer for this question number 1, A and B. Then number 2, explain between B and C which line has a higher frequency, which one has a higher energy frequency. So the difference of the frequency in here will depends on which one has a greater difference of energy level. So in here we expected that B has a higher frequency compared to C. B has a higher frequency compared to C. Sorry for that. B has a higher frequency compared to C. I'm so sorry for that. Because the energy level difference B is greater. Okay, the level of B is greater, so that is why you expect B to have a higher energy levels compared to C, because the difference of energy level is greater. So that is how you're going to answer for this one. Of course, you can use calculation to prove, but since the question only asks you to explain, so there's no need for you to go through all the calculations because this will take a lot of time. Okay, so the best answer in here will be B. Yeah? Okay, so C, using Ripple equation, calculate the wavelength produced in the transition spectrum of T. Given to you, Ripple constant is 1.097 × 10⁻⁷ meter minus 1 per second. Okay, so here you have to memorize the Rydberg equation. So 1 over lambda is equals to RH times 1 over n1 square minus 1 over n2 square. Or you substitute into your 1 over lambda. Okay, and then as I always tells you, the 3 marks goes to equation, substitution, and then answer. Okay, so you don't need to show us how you actually calculated the lambda, just substitute accordingly, and you'll be able to get your answer as 1280 nanometer. Do you really need to actually live in nanometer? Actually, no need. Even if you answer as this, sorry. Even if you answer as this, let's say 1.28. times 10 power of 6 meter. But also it's okay, so it doesn't really matter. Okay, so this is for number 1. Then immediately we goes to number 2. So the number 2 is proton number of chromium is 24. Write the electronic configuration of chromium atoms. So how to write the configuration of chromium atom. So you have to know how to write the electronic configuration of chromium atom with the proton number 24. So we want electronic configuration, so it should be a full one. So it should be a full one. So how are you going to write electronic configurations for the chromium atom? So you should write as okay, you should write as a full electronic configuration where you are going to write as you have to start as 1 S2, 2 S2 already 4, 2 P6 already 10. Then you shall have 3 S2, which is already 12, 3 P6, which is already 18. And then here there is an anomaly here, which is 3D5 and then 4 S1. Okay. Okay, but because they want electronic configuration, so you must write in the full form of electronic configuration. We do not accept if you write like this. I see that some of the books, they sometimes love to put AR 3D5 or S1. So you cannot write like this. Please do not write like this. Is it okay if I write 4S1 3D5? Instead of 3D5, 4S1, I mean, you write until here, then you write 4S1, 3D5. Is it okay or not? It is okay, no problem. Okay, you can still write like that. Okay, okay. However, when it becomes ions, so when they become ions, electron must be first removed from the 4s orbital. So this will make the electronic configuration of the chromium 3 ion as 1 S2, 2 S2, 2p6, 3 S2, 3p6, and then 3d3. Okay, so this is how you are going to write for chromium. Okay, so this is how you answer for A. Then for B, in the energy level diagram below, sketch the energy level diagram of 3D and 4s before and after electrons is filled. So before electrons is filled, you have to always remember by heart that energy levels of the 4s is lower than the 3D. Energy level of 4s is lower than 3D. So you have to write out accordingly to the energy levels. Okay, so that is the energy level for 4s and 3D. However, after filling in electron, after filling in electron, 4s will be greater than 3D in terms of energy level, slightly higher. So you'll be able to right. Okay, and in here comment on the irregularity in the filling of the chromium atom. So what are the irregularity in here? Number one, you will notice in the filling of the electronic configuration of the chromium, 3D is half filled. Okay, 3D is half filled, while 4s is single filled electron. Do you notice that? So that is the 2 points that you have to comment on the irregularity. So it's you have to mention that 3D is half filled as it has extra stability, and then the other point is saying that 4s orbital is filled with single electron because in a normal trend you have to fill in the 4s orbital before you're filling in 3D. You have to fill in fully 4s before filling 3D, isn't it? So supposedly it's 3D 4s2, but because the half fill orbital is more stable, so that is why you have to fill in as 3D 5 4s1. So that is how you answer for question number 2. And as for number 3, sulfur can be easily obtained from the deposit of volcanoes. Write the electronic configuration of the sulfur atom. So this one should be quite easy for you. You should be able to write the electronic configuration of sulfur. If you don't know the proton number, you can always check the periodic table behind there. So you have 1s2, 2s2, 2p6, 3s2, 3p4. Okay, then number 2, if you can, you highlight, you must draw and label the shape of all orbitals containing valence electron. So the valence electron is inside the orbital of 3s and 3p, so that means you have to draw and label all shapes. So whenever you are drawing the drawing this one, you have to draw in the three-dimensional array. So when you are drawing in three-dimensional array, you must be able to draw the axis also. So you have axis X, Y, and Z. So this will be how you draw. So 3S in here is a sphere, if possible, label. The question also said label. So you have a 3S. And then in here, it is a dumbbell shape. So when you have at p-axis, this is 3px. If you lay at the y-axis, this is 3py, and you lay at the z-axis, this is 3pz. Okay, so you have to label accordingly. Okay, so not necessarily as beautiful as this, but as long as the axis is correct, then it should be no problem at all. Okay, okay, so this is for number 2. And then number 3, state one orbitals of the sulfur atoms that are filled according to Hund's rule. So Hund's rule stated that in a set of degenerate orbitals, electron must be filled with single electron before pairing. So in another word, Hund's rule only apply to those orbitals with more than one orbitals, okay, at the same energy levels, and they must be paired with a single electron. So therefore, the orbitals of the sulfur that will fulfill according to Hund's rule, either you write as 2p or 3p. Either one is okay, because this only say one of them. Okay. So that is how you're going to answer for 3. So they are going to continue with B. Sketch the energy level diagram of orbital of an atom other than hydrogen with principal quantum number of n1 to n4. So n1 to n3. So for n equals to 1 to n equals to 3, you sketch the energy level diagram for multiple atoms. So you have to draw according to the Aufbau principle. So Aufbau principle stated that electron filling in from the lowest energy level, where you have lowest energy level is 1s, 2s, 2p, 3s, 3p, and not to forget 3D is also part of the energy levels inside n equals to 3. So most of the students will tend to neglect the 3D in here, but if you miss one, then that's why you lose 1 marks in here. So you must include the 3D orbitals. Now, why is you'll be wondering why is it that the question specified that other than hydrogen atom? Because in hydrogen atom, when it is only single electron, energy level diagram looks like this. If you still remember, okay. So you have n equals to 1, n equals to 2, n equals to 3. So this is for hydrogen atoms. So in here, there are no energy differences in between each of the orbitals, because for a single electron system, so all energy levels are the same. So this is the differences between a multi-electron system and one electron system. Okay, so that's why usually the question will specify other than hydrogen atoms. Okay. Okay, so that is for number 4, and then we continue with that's for number 3, and then we continue with number 4. Sodium-24 isotope is used in medicine to study the blood circulatory system. Write the electronic configuration of the sodium-24 isotopes. So how are you going to write the electronic configuration? So you have to write as 1s2, 2s2, 2p6, 3s1. And number 2, how many orbitals of sodium-24 are fully filled? So regardless whether it is isotopes or not, the number of electrons should be the same. So therefore, the number of the orbitals should be the same as the above. So 1s contain 1 orbital, 2s contain 1 orbital also, 2p contain 3, so 3s contain 1. So total orbitals is 6 orbital. Fully filled. Fully filled. So fully filled, that means it does not involve the 3s1. Sorry for that. Fully filled, so that means there's only 5 orbital left. Okay. Okay, so 5 orbital left. So the answer is 5. Okay, then number 3, state the orbitals of the sodium-24 ions which contain valence electron. This is a very tricky question because now the question asks about ions. Okay. So when ion, sodium will usually form sodium plus. So sodium plus means what? Sodium plus means that 1 electron from the 3s will be removed. So this will make the valence electron to become 2s2, 2p6. However, if you write 2s2, 2p6, the answer will be wrong because the question says state the orbitals with valence electrons. So they just want orbital. They don't want you to write the electronic configurations. So therefore, you have to write as the atoms, so valence electron. So the valence electron of the orbitals are at 2s and also 2p. Okay. Okay, so that is for number 3. And number 4, state 1 reason why sodium-24 is rarely found in naturally. So you have to understand why is it 24 is little. So either you say is that it has a short half-life or disintegrate easily. Okay, so you can also say that it is radioactive also can, no problem. Okay, but usually we will recommend students to write it has a short half-life. Yeah. Okay. Okay, so that will be for question number 4. Okay, then we goes to straight away question number 4b. The figure below shows several lines of the Lyman series in the emission exposure spectrum. So energy level diagram below shows how the line marked Z is on the spectrum. So in here, it is a Lyman. If you look carefully at the statement here, it already stated that it is a Lyman series. You already stated that it's Lyman series. Okay. Okay. So in here you have to understand that this is the first line, and this is the second line, and this is the third line. So when the third line is 4 from energy level n equals to 4 to n equals to 1. So you have to label like this. Okay. So n equals to 4 to n equals to 1. So this is how you got the line Z in there. Okay. Okay. So that is for number 1. Okay, and number 2, draw an emission spectrum from a helium ion. So helium plus. So helium has a proton number 2. When you form plus, that means it will make the electron equals to 1. And this line spectrum is the same for all single electron system. Okay, the line spectrum should be the same for all single electron system. So that is why it should be the same. So your line spectrum will more or less be the same as the above just now this one. So just redraw the diagram and then you get your 1 marks in there. Okay. Okay, so that is all for question number 4. Then we continue with question number 5. If 2 or more orbitals with equal energy are available, the orbitals are each filled with 1 electron, with the electron having parallel spin before second electron of the opposite spin is added. So name the above rule. So this is obviously a Hund's rule. Okay, so 1 mark stating that is Hund's rule. Hund's rule, not Pauli exclusion principle. Sorry, yeah, sorry for that. Typing error. Hund's rule. It's supposed to be Hund's rule. Sorry, yeah. It's supposed to be Hund's rule. Okay. Okay, so that is supposed to be Hund's rule, 1 mark. Okay, number 2, draw a diagram showing valence electron of an atom with a proton number 29. So valence electron of atom X with proton number 29, because they only one valence electron. And if you look at the question carefully, they only want this diagram, draw a diagram showing valence electron. Okay, so you draw as in like this. So 3d10 for S1. And then number 3, state the number of unpaired electron in atom X. So the number of unpaired electron in atom X is 1 only, because only 4s is not paired. So there's only 1 valence electron left. Okay, so that is for number 5a. Then we have number 4. Based on your answer in 3, state the magnetic properties of the atom X. So since you have at least 1 electron which is unpaired, so this type of magnetic property, we call it as a paramagnetic property. Paramagnetic. So, and then you have another one which is called as a diamagnetic. So diamagnetic is where when you have all the electrons in the orbitals are paired. Okay. Okay, so this is for number 4. And then for number 5, X can form X plus by donating 1 electron from the outermost shell. State the valence electron of X plus and deduce the magnetic properties of the X plus. So if X is 3d10 for S1 just now, okay, so the X plus is 3d10. So if 3d10, the magnetic properties changes because all of them are filled with pair of electrons, isn't it? So therefore we say that it is a diamagnetic. Okay. And last but not least, B, covalent bond in a molecule absorb radiation in the infrared region and vibrate in the characteristic frequencies. The carbon monoxide bond, carbon oxygen bond absorbs radiation of wavelength 0.96 nanometer, what frequency in second -1 corresponds to that. So first of all, you have to calculate the frequency first. So you use F equals to C over lambda, where you F is 3.00 divided by the wavelength 0.96 nanometer. So when it is a nanometer, so you have to remember the terms nanometer in here is times 10 power of negative 9. And 10 power of negative 9. So therefore, this will make your frequency equals to 3.1 times 10 power of negative 17. So when you have F equals to 1 over 17, so that will be how you answer for question number B. Okay, so that is for number 4, F5, and then we go to question number 6. A part of the periodic table is shown in the diagram below. So you have A, you have B, C, D, E, F, G, H. So all these are not represented by the actual symbol. Based on the periodic table, state an element from X block. So the element from X block is A, and then B. Number 2, why these elements are from the same group. Write the valence electron of both elements with your answer. So as you can see clearly in here, the one that has from the same group in here, which one? You see clearly they are from block B and also block F. Okay, so you have to write the valence electron. Okay, where E here has a 2s2, 2p5, F here has 4s2, 4p5. Okay, so with that, that is for 4A. And then 4B, write electronic configuration of B. Justify your answer with explanation on how the valence electron are filled in the orbital. So you have to use any methods that you want to explain how does the electrons are filled. So you have to first answer what is electronic configuration of B. B, so 1s2, 2s2, 2p6, 3s2, 3p6, 3p5, 4s1. And then we say that how to explain this, because half-wave 3D orbitals are more stable. Okay, so that is how we survive number 3. Okay, last but not least, number 4. One of the ion of H is isoelectronic with G. Deduce the molecular formula of ion H and write their electronic configuration. So in here, if your H come to H plus, so the electronic configuration are not valence electron. They want electronic configuration, so this one is correct. Okay, so with that, that is for question number 6. Okay, then we go to question number 7. The frequency in the Lyman series shows in the spectrum of the hydrogen are given below. You have 2.466, 2.923, 3.003, 3.157, 3.197, 3.221, 3.2337 hertz in here. Now, number 1, on the energy level diagram, draw arrows to illustrate the electronic transition of the hydrogen atom that corresponds to the frequency in here. So you have to draw minimum, you have to draw at least 3 energy levels. So you show how N1 falls to N3 falls to N1. Now I draw for N2 lower than N1, and here you also expected to give this mass spectrum in here. Okay, you are also expected to give a mass spectrum in here. So you draw accordingly, then you remarks in there. Okay, and number 2, from the frequency of the leaves in a human series given, calculate the energy, remove 1 electron from hydrogen atom. So you use E is equal to 6.63 times 10 power of negative 34 multiplied by the speed of light 3.27 times 10 power of negative 10. Okay, then using the then you get your answer as 2.146 times 10 power of negative 18 joule per electron. Okay, number 1, using suitable principles or rules, explain configuration of lithium atom. So lithium atom is 1s2, 2s1. So therefore, based on the Pauli exclusion principle, each orbital is occupied by a pair of electrons with opposite spin. And last but not least, you can explain based on the alpha principle. The alpha principle are electronegative orbitals from the lowest energy level. So in the definition of the alpha principle, this keyword is very important, lowest energy level. Okay, so with that, that is for question number 7. Okay, so I guess that is all for my sharing session today for structure questions. So if you have any question, you may leave a comment inside the YouTube, and then I'll try my best to reply as soon as I can. So hope you all enjoy the lesson. If you like my lesson, please remember to share with your friends. You can always purchase the copies of books from Shopee. So you search Shopee, you search Stpm semester 1, then you'll be able to see the series of books that I show. Okay, so I guess that is all for our lesson today. So see you all next week.